Hello everybody. Today we talk about FPU design. What is FPU? It's a floating point unit. Floating point unit is one of specialized CPU chip, and usually it's much bigger hardware than CPU. The RISC CPU is smaller than FPU. The reason? The FPU has huge set of execution unit. It's used for scientific calculation, and existing FPU unit is also used for AI calculation, but it's overkill. I tell you why the AI shouldn't use the FPU, instead make its own specialized processor unit, and that's another subject. We are not getting into AI chip design yet. Today is FPU, and FPU is actually scientific calculation mostly, and it's a rational number calculation, like 1.25 plus 0.026. This kind of calculation that cannot be done by integer. Typically the general purpose CPU can handle only integer and logic operation, but this kind of number, this rational number calculation, usually use FPU. And you don't have to have a FPU, because general purpose integer based CPU can have a software package. That software package calculate this kind of operation. It's just very slow. In order to do the high performance the rational numbers calculation, then you need a FPU chip. So in this sense, it doesn't make sense to use field programmable chips to make a FPU, because the performance is the issue. Then here, the performance, if you don't get the performance, if you use the field programmable those or logic array, you can't get the highest performance, and then what's the point of making a FPU chip? Just use software package, right? So naturally the architecture is going to be like pipeline. And what pipeline means, the minimum clock speed to perform addition and multiplication, and division is totally another subject. This hasn't been really resolved in the industry, how to do divisions. With just scientific formula, we avoid divide as much as possible and try to do everything by add and multiply. Okay, so how do you represent this kind of number in, say, 32-bit memory, right? So there is a IEEE standard format, and the format said you have a sign bit, and 32-bit you have 8-bit, and this is exponential part, and the remaining is going to be the number 23-bit. So it's like you have 23 bits of number multiplied by e to the x. This is a x up to 8. Okay, and you have a sign plus or minus. This is a sign bit. Okay, so this is total 32 bit. And represent this kind of number. So there are a lot of number, it doesn't fall into this range. So obviously we have to deal with overflow and underflow. If number is smaller than smallest, then it's underflow. A calculation result cause the number you can present bigger than this number, then it's overflow. Okay, and let's think about what is the largest number. So of course this is it, right? And 23 bit, actually 23 bit assume 1 in front, which is not expressed. So this is a format defined by IEEEs. You have 1.23 bit. So this is under decimal number. Okay, so largest is going to be 1, 1, 1, 1. This is 32 bit, 23 bit. So this is a largest number, right? What is the smallest number? It can be positive or negative. It's symmetric, right? And smallest number is going to be e, exponential is 0, and this is not multiply, actually this is the way, it's a digit, sorry. So e 0, and smallest number is, you must have a leading 1 and all 0, right? So actually smallest number is you use 8-bit 2's complement, then you can have a number from the largest number is 0, this 7. So it's like total number is 8-bit is like 255 numbers there, right? So it's going to be, if its top bit is 1, 128, so 127. And negative, using this 8-bit 2's complement number, it's the smallest number, lowest number, I mean, this is -1, and go all the way to 0.0000128, right? So total you have 255. Yeah, that's correct, because number you can express is 255 in the 2's complement. Now this is going to be -128. So 1 actually times 2 to the 128, right? Actually not times, this is a digit. So this is the smallest number, lowest number, right? And it can be plus, minus. This is very close to 0. And now floating point has no 0, because you have a leading 1, so it's always non-zero. Okay, so the floating point, you cannot have a number 0. In the scientific calculation it sounds strange, but the closest to 0 is this number. Okay, now is this accurate enough? When you worry about accuracy, there are a lot of issues, and IEEEs specify overflow, underflow, and nearest, rounding to the nearest, truncate, round up, round down, all kind of things. But rounding to the nearest is a big problem in the high speed floating point, because after you calculate, say you got finally answer X and has some number below, and you have to round it. This rounding may cause carry propagate again. So after calculation, you have to do one more time, add 1, and what if the shifted become 1 0 point something, then you have to shift the number again. If you shift the number again, 1 bit go below, you have to do rounding kind of thing. So round to nearest is a lot of problem. So in the high speed FP, usually you use only truncate, because of the round to the nearest, the amount of hardware may increase by 30% or more, and performance drop. And which one you want to take, performance or accuracy? Okay, and when you worry about accuracy, you have a remedy. What you do is to take double precision, FP. And what the double precision? It's a 64-bit. So you have much more finer grain of real number, the rational number. This is the 11-bit for the exponent, and you have a 52-bit for the after leading one number. So this is super accurate. And in the scientific calculation, when you need accuracy, double precision floating point unit. So then, do you make two different chips? Now actually, the chip is made by double precision, right? And there is a command, conversion command, double precision to single precision, and conversion single precision to double precision. And when this command is executed, then usually you have a choice of round to nearest, round up, or truncate kind of option. So if you worry about the accuracy, what you do is use a double precision, and the chip, FP chip, should be a double precision, and provide a double precision using single precision number, because 32-bit is going to produce, when you do multiplication, 23 plus 23, 46-bit result. Okay, so single precision's multiplication already generate a 46-bit number. Then you decide to do round up or round down or round to nearest when you convert it back to single precision result. So the instruction should be provided to convert this. Okay, then we start talking about how to design the, say you have x e to the y, right? this is the floating point number. So you have to put x1 to e1 plus minus doesn't matter, because this can be plus number, this can be minus negative number, 2 to the y2. Now you cannot just add like that, right? You have to change to 1.23. The yeah, you have to align the point here to do the add, right? You don't do this like you used to do in integer plus minus. Okay, this doesn't work. You have to align it, right? So in order to align, both has the leading, the x1 has a form of 1 point so and so, x2 also has 1 point, this kind of number, right? So first you have to compare this, right? So you have to do 1 minus y2, and this is a 2's complement, so if negative, convert is positive, right? And this positive number, say this is shift right, okay. So when you have this number x1 e 2 to the y1 and x2 e 2 to the y2, first thing is you have to shift the number to the right. And how much shift amount? Okay, sorry, I'm getting so many interrupt. Let's see. So what we have to do is to compare the exponent portion first and convert into positive number, and use this as the amount of shift, and you have to shift right. So it's going to be 0 point so and so 1 0 1 1 0, this kind of number, and this number to this number, which is 1 point, is going to be added or subtracted. And if you use ternary logic, the subtraction is just add, the reverse the bit, positive bit and negative bit, and add 1, right? So you perform this. Now you have to be careful about this. After you perform this, there are some complication. When 1y minus y2 is less than 2, that means 1.0 something and 0.1 something, right? Now there is a chance that this part is massively wait a minute, let's see. We have to consider this case, right? The difference is only 1, and if it's 1, the case like this. So after subtract or add, it may shift right or left by 1 in order to bring back the format to leading 1, so and so, right? When this is 0, there is a chance that this part is eliminated, and it may end up with, there is a chance that the answer end up to be 1, 0, 1, 1, so and so. So the no more leading 1, okay, just shifting by 1 will not bring this back to the original. So in this case, we have to worry about bring this format back to the leading 1, the standard floating point unit. So we need this leading 0, leading bit detection. So leading bit detection. And this logic design is a little bit problem because you don't know how many bits are 0. If you try 1 by 1, it costs 1 clock each and 64 bit. This gonna be very slow floating point unit. Okay, so in order to use a pipeline, we assume 1 is here and assume 1 is here. So every actually it's not 52-bit, sorry, 52-bit, the floating point. 52-bit cases, massive parallel operation, and pick the 1 by multiplexer to the correct one. Maybe leading bit is here. Okay, this is going to be huge amount of hardware, and plus it's not that fast either. Okay, so what we do is we take a shift 1, otherwise no more shift kind of logic. Okay, so let me show you. This is the shifter logic. We take this part. Okay, and say we have a P0, P1, P2, P3, and this is gonna be P1, means it's shifted, right? And P2 and P3, so and so. So this guy is a shift. This guy is a shift or a non-shift. It just pass through. So we make this array of 1-bit shift, and after shift, if this happen to be 1, we're shifting this way, and the 1 comes in, then from here it's going to be signal to the next no more shift, right? Capture the 1. Once this 1 is captured, the flip-flop, then this flip-flop stay on, so it's all passed through. Until we find the leading bit, shift one bit, and the shift one bit is just in the CMOS 2 gate. So data pass through this reading bit detection. Okay, and this can be improved by, instead of detecting only one, detect two. So this array, the size of array become half. Then later you make this adjustment, 1 bit adjustment. Okay, it's complicated logic, but it can be done. So we have to do this in order to bring back, and after you bring back to reading one number, right, this decoded shift amount has to be added to Y, then check overflow or underflow. If this happens, then exception occurred, right? Then program does not take the result of calculation anymore. So the program is going to go back and handle exception handling process. Okay, so finally we bring it back to this format. So again, this difference is less than, it's 1. There is a chance that we have to shift right or left, depend on addition, 1.0 and 1 is added, then it's going to be 11 point whatever, so we have to shift this way. If it's subtraction, then it's going to be 0 point something. That means we have to shift a bit here, and actually this may cause more shift. So if it's 1 and subtraction, we have to go through the same process of reading bit detection process, and that's a lot of gate the signal go through in order to have the final this format. Okay, so that's addition. So we're talking about multiplication next. Multiplication is y1 plus minus y2 is going to be negative, and this is going to be new result y, right? So when you have y, the sign doesn't matter. It's a sign. If it's both positive or positive, if one side is negative, it's negative. So exclusive OR of sign bit is going to give you the sign number. So this exponent portion has to be subtracted, not subtracted, added for multiplication, right? x1 times x2 e to the 2 y1 plus y2. Okay, so this is going to be new exponent, and multiplication is much more straightforward. This is x1, and x2 you write up this way: 1, next number, next number, next number, and this gonna be multiplied. This bit is multiplied to this, and we have to add them all. And this is again wallet tree, and the wallet tree using ternary logic is going to shorten the tree lengths by quarter, because each wallet tree is adder, half a adder has one additional input. It can add more at the same time, and also its adder itself is faster. So multiplication speed is faster using ternary logic. The result is going to be double side. If this is a 52, it's 104 bits. Now again, we use truncate, and you worry about, well, IEEE said we should provide nearest run nearest to, but well, it's going to be a lot of hardware to be added, and cycle time for the calculation, and sometimes it's not worth it. So it's matter of conforming the standard, and also accuracy issue. If double precision, if still double precision is not, you worry about accuracy, the quad precision, and there's nobody make this hardware, and quad precision is done by software package. And software package is extremely slow, but you get the very accurate result. So accuracy is number one priority, the software package to be used. Otherwise, this hardware is going to provide the flow through. You have execution unit, you put number to number, the answer come out within maybe fast chip like 3 to 5 clock cycle in pipeline fashion. So if you have a lot of number to calculate, you can just keep feeding and keep getting it. Every clock cycle you get floating point calculation result. Okay, so that's all for today. I hope you get the idea about what floating point coprocessor does. Usually it's a additional processor and expanded instruction set for the RISC-V, and RISC-V, you have a choice. You use software package, or you add this massive hardware to do fast calculation. As I said, if you do AI using RISC-V, floating point is not the way to go. Floating point is for the more accurate scientific calculation, and the AI, you don't need that accuracy. What you do is to check the tendency. So we get into that probably in the future video. If you think this video is useful, please subscribe. Make sure you get notice for the future video.